Oftentimes we are interested in studying functions f which are defined and holomorphic on a set omega minus a set S, where S is called the set of singularities of f. This week we will be discussing the notion of singularities of a holomorphic function. Singularities come in varying levels of severity and we will be exploring them one by one. I have been using the word singularity many times, so let me begin this week by defining what is meant by a singularity of a holomorphic function. So, isolated singularity, that is what we will be defining. We say that a point z0 is an isolated singularity of a function f if f is defined and holomorphic in a punctured disk of radius r around z0. If f is holomorphic on d z0 r minus z0 for some r positive. We do not know about whether f is defined at the point z0 or not. We know that in a punctured disk of radius r around z0, the function is defined and it is holomorphic. If this happens, then we say that the point z0 is an isolated singularity of our function f. Let me give a few examples to clarify this notion. For example, if you consider the function f of z to be equal to e to the power z minus 1 by z. This is defined where? Away from 0. On c minus 0, we define our function f of z to be equal to e to the power z minus 1 by z. Notice that here we could take any r positive, and away from 0 in d0r minus 0, 1 by z is defined and is holomorphic. Or by applying the quotient rule, we can check that e to the power z minus 1, which is an entire function, divided by z, which is also an entire function, is holomorphic away from 0, the zeros of the identity function. So this is an example of an isolated singularity at the point 0 of the function f here, which is given by e to the power z minus 1 by z. Notice that division by 0 is not defined, and therefore we do not know yet how to talk about what is the function f at 0. Another example, so this is one example, let us look at another example. Let f of z be equal to cos of z by z. Again, we do not know about division by 0, so again this is defined on c minus 0. The quotient rule can be used to establish that on any punctured disk around 0, by removing 0 of course, the function f is defined and is holomorphic there, and we do not know what the function is at the point 0. Another example would be to consider y always at 0. Let us change the point where the singularity is being considered. One shouldn't get the feeling that always singularities will be around 0. So, let us consider this function e to the power 1 by 1 minus z. Okay, let us see where it is defined. This is the composition of the function e to the power z with the function 1 by 1 minus z. And 1 by 1 minus z is a rational function which is defined and holomorphic away from z is equal to 1. So, this is again defined and is holomorphic by the chain rule on c minus 1. And we do not know how to define the function at z is equal to 1, because 1 by z minus 1 does not make sense at z is equal to 1. Right. So, these are examples of, so let me see, let me write down the singularities. In examples 1 and 2, the functions f have singularities, isolated singularities. So, sometimes the word isolated is dropped, but it is always the isolated singularities that we will be referring to when we say singularities. Let me just underline the word that we have used. Sometimes the word isolated is dropped to talk about isolated singularities, and just singularity is used to refer to them. But whenever we use the word singularity, we mean isolated singularities in this course. So F have isolated singularities at z0 is equal to 0. And in example 3, F has an isolated singularity at z0 is equal to 1. Many times we will be interested in studying how our holomorphic functions behave as we approach the singularities. And by studying this particular behavior, we will be able to classify the different types of singularities that a holomorphic function can have. We will be doing that in this week. Let me begin this classification by studying what is called as the removable singularity. Let me define what a removable singularity of a holomorphic function is. Of a holomorphic function. So notice that this is the attempt is to classify isolated singularity. So let's begin with an isolated singularity of function f. So let z0 be an isolated singularity of a holomorphic function. We say that the point z0 is a removable singularity if our function f can be extended to the entire disk dz0r. Remember that the moment it is an isolated singularity, there is some r such that f is defined and is holomorphic on dz0r minus z0. Removable singularity says that we can extend it to the entire disk dz0r. So let me write that down, and let me write down what it precisely means to say that it can be extended to dz0r. R positive such that f of a holomorphic function, let me call that function something, let me call it f, i.e. there x is R positive such that f is defined and is holomorphic in fact on dz0r minus z0. We say that z0 is a removable singularity. This singularity can be removed, that is what it means. Removable singularity of f if there exists a function g on dz0 r g which is holomorphic on dz0 r g which is holomorphic on dz0 r and such that f of z is equal to g of z on dz0 r minus the point z0. So essentially the function g is f on dz0r minus z0. At every point on dz0r minus z0, the function g is the same as f. But we didn't know whether our function f could be defined on z0 or not because it was an isolated singularity. So it is a removable singularity if we can indeed get hold of a function which is defined on the entire disk dz0r and which coincides with f on the punctured disk. Let us do the exercise of looking at our examples. Let's revisit our examples which we had given, and let's see whether these examples are removable singularities or not. That's the next venture we will be indulging in. So let us revisit the example. So notice that when I said that f can be extended to dz0r, it means that there exists one such function g. That's precisely what it means when I say that the function f can be extended to dz0r. Okay, so the first example, if let's go back and check what it is. If the function is e to the power z minus 1 by z, let e to the power z minus 1 by z be the function f of z. The question is, do we have a function g which is defined in a disk of radius r around 0 such that on d0r minus r minus z0 minus 0 in this case, z0 is 0, the function g matches with f. Now notice that we could pick any r, so because it's defined on c minus r, let r greater than 0 be a real number, be any real number. Now notice, remember that we know e to the power z is an entire function, and because of that we know that it has a power series expansion around 0. So we know that e to the power z minus 1 also has a power series expansion around 0. Notice that in d0r we have e to the power z minus 1 to be equal to summation z to the power n by n factorial, where n is going from 0 to infinity. That is the power series expansion of e to the power z minus 1, which is just going to be equal to summation n is equal to 0 to infinity, not 0, the first term is going to be cancelled and we will have z to the power n factorial. Now the summation going from 1 to infinity. Let us define g of z by using the power series summation n is equal to 1 to infinity z to the power n minus 1 by n factorial. Let us define a power series like this. It is a simple exercise for you to sit down and check using maybe the ratio test. I have even given you the hint. Check that g is an entire function. In fact, g is holomorphic on t z0. Here z0 is 0, so let me write d0 comma r. So this has isolated singularity at 0. That is what we are studying, right? We are interested in checking whether this isolated singularity is a removable singularity. Now g being holomorphic on d0r is a simple exercise. Let me leave that to you, and hence on d0r we have, for z in d0r, z times e to the power z minus 1, or rather let me look at what is z times g of z, that is equal to z times this power series. Because it converges absolutely, we can take the product in, and this is going to be equal to n is equal to 1 to infinity z to the power n by n factorial. If you notice, that is precisely e to the power z minus 1. Hence, z times g of z is equal to e to the power z minus 1. So, for z not equal to 0, we can divide by z. We have, in fact, for z not equal to 0, in particular on d0r minus 0, we have g of z is equal to e to the power z minus 1 by z, which is equal to f of z. Hence, we have indeed found out a function g which is defined on d0r, holomorphic on d0r, and on d0r minus 0 it is equal to f. So, that means f has a removable singularity at 0. That is good. So, before we actually look into the second and third example that we had given, one key thing to note is that the existence of the function g tells us that as we approach this singularity, if at all a point z0 is a removable singularity of a function f, the existence of the function g tells us that as and when we approach the singularity z0 in dz0r minus z0, we have to end up with g of z0, right? Because g is defined on dz0r and it is holomorphic, in particular it is continuous. So, if f has a removable singularity at z0, a necessary condition is that the limit as z going to z0 of f of z0 exists. Let me just note that down. Note that if an isolated singularity of f of isolated singularity z0 of f is a removable singularity, then the limit as z goes to z naught equal to z naught of f of z exists. This limit should necessarily exist, should be a complex number. In fact, it will be g of z naught, where g is the function which extends f to the entire disk dz0r. With this observation in the background, let us now revisit our second example. What was our second example? Cos of z by z. Let us look at f of z to be equal to cos of z by z. F has a isolated singularity at 0 in this case as well. Let us check whether this isolated singularity is a removable singularity. To do that, notice that cos of 0 is equal to 1, and because of that, because cos is an entire function, it is continuous. Cos of z is a continuous function, and therefore there exists some capital R, and hence there exists capital R greater than 0 such that d0 on d0 r absolute value of cos of z is less than m for some m positive. It is bounded in a neighborhood of 0. This is possible because cos is a continuous function. It is in fact holomorphic. Now consider the limit as z goes to 0 of the absolute value of cos of z by z. It is a simple exercise to check that this is equal to infinity. So, in particular, we will not be able to get hold of a limit as z goes to 0 of cos of z by z. So, if 0 were to be a removable singularity, the limit should exist. Limit z going to 0 of absolute value of cos of z by z should exist, and we just observed that this limit blows up, and hence 0 is not a removable singularity. So, immediately we do have cases, very simple cases, where it is not removable at all, the singularity is not removable at all. Let us revisit our third example. What was the third example? The third example was e to the power 1 by 1 minus z. Let f of z be equal to e to the power 1 by 1 minus z. This has an isolated singularity at z is equal to 1, right? And let us see if we do have a limit as we approach 1. What we will do is we will consider two different sequences. The first sequence being Zn, which is equal to 1 minus 1 by 2 pi I n. So, if you notice, this is a sequence which converges to 1 as n goes to infinity. And what is f of Zn? F of Zn is equal to e to the power 1 by 1 minus Zn, which is 1 minus 1 by 2 pi I n, which is equal to e to the power 2 pi I n, which is equal to 1. And hence, the limit as n goes to infinity of f of Zn is equal to 1. So, we are indeed getting hold of some limit as we approach 1 along this particular sequence. However, let us consider another sequence Zn prime, which is a slight variant of the above. Let me just add up an pi I by 2 to this. This is our Zn prime. And let us see what is f of Zn prime now. F of Zn prime is going to be equal to 1 by 1 minus 1 by 2 pi I n plus pi I by 2. Now, notice that Zn prime also converges to 1 as n goes to infinity, and we have this is equal to f of Zn prime is equal to, this is e to the power this particular number. I hope I did not miss the e to the power earlier. No, I did. So, this is going to be equal to e to the power 2 pi I n plus I pi by 2, and that is going to be equal to e to the power I pi by 2, which is equal to I. So, if you notice the limit as Zn prime goes to n goes to infinity of f of Zn prime, this is equal to I. So, we go along two different sequences, we are getting two different limits. So, the limit does not exist as we approach 1 along, because its different values when we approach along different sequences. So, this limit does not exist. So, the necessary condition for a function to have an isolated singularity as a removable singularity is violated. F does not have a removable singularity. At z is equal to 1. We saw that the first example did have a removable singularity, and the second and the third singularities were not removable singularities. We will see eventually that the second and the third examples are different types of singularities, but we will come to that later. Okay. One necessary condition we observed for a function f to have removable singularity is that the limit exists as we approach the singularity. We will now give a weaker condition to check that indeed an isolated singularity is a removable singularity. This is called as the Riemann removable singularity theorem. Let me write the statement down. Riemann removable singularity theorem. So, this is a characterization of removable singularities. Let Z0 be an isolated singularity of a function f. That means that there is a IE, there exists R positive such that f is holomorphic on dz0 R minus z0. Then f is a removable singularity. That means we can get hold of a function g which extends if and only if f is locally bounded around z0. So, what does it mean to say that f is locally bounded around z0? It means that in a punctured neighborhood around z0, our function f is bounded. Let me write that down. That is there exists epsilon positive and m positive such that absolute value of f of z is less than or equal to m for all z in dz0 epsilon minus z0. Remember that the function is not defined at z0, so we will not be able to say anything about the value of f at z0, but away from z0 in a local neighborhood we can bound absolute value of f of z. Let us give a proof of this statement. So, again, revisiting the statement of the Riemann removable singularity theorem, the key thing to note is that getting hold of a function g which is described in the definition of a removable singularity is not very easy. Many times it is not very straightforward like we saw in the example. The first example, it was quite easy to get hold of one such function. Many times it is not easy to get hold of a function explicitly, and this theorem helps us in concluding, even if we are not able to get hold of an explicit function g, this tells us whether we can conclude directly that it is indeed a removable singularity. Let us give a proof. One side is easy, so it is an if and only if statement. So, the forward direction would be to prove that if our function f is having a removable singularity at z0, then it is locally bounded. So, assume that f has a removable singularity hence there exists g defined, g holomorphic in fact, on dz0r, and since g is continuous at z0, g is bounded in a neighborhood of z0, which tells us that f is bounded in a neighborhood of z0, in a punctured neighborhood. In a neighborhood, let me precisely write what the neighborhood is, dz0 epsilon, and this will be bounded in dz0 epsilon minus z0 because f is exactly equal to g on dz0 minus epsilon, dz0 epsilon minus z0. So, the forward direction was straightforward. The work comes in proving that if it is locally bounded, our function f has a removable singularity at z0. So, let us now assume that f is locally bounded. In a neighborhood of z0. Locally bounded means it is in a neighborhood of z0 anyway. Let me specify what the neighborhood is. In a neighborhood dz0 r minus z0. Alright, so let us now define a function on dz0 r. Define g, or maybe not g, h from dz0 r into c by h of z to be equal to z minus z0 times f of z, when z is in dz0r minus z0. Notice that f is defined on dz0r minus z0. Z minus z0 is an entire function, so the product makes sense in dz0r minus z0. and there let us define h of z to be exactly equal to z minus z0 times f of z, and at the point z0 let us define our function h to be equal to 0. Let me give you a simple exercise to conclude that h is indeed a holomorphic, is a continuous function. The fact that f is locally bounded around z0 will have to be very crucially used to conclude this. We will now prove that h is indeed a holomorphic function. That is the major part of this proof. So, let us see what happens if h was holomorphic. If h was holomorphic on dz0r, what can we conclude? Then, because a holomorphic function is complex analytic, there exists a power series expansion of h on dz0r given by h of z is equal to summation a n z minus z naught to the power n, where n is going from 0 to infinity. But the key thing to note is that h of z0 is equal to 0. You notice how was h defined? The function h did satisfy the condition that h of z0 is equal to 0. Remember that we are doing all these things by assuming that h is holomorphic. We have not checked that yet. We will do that eventually, but if h were to be holomorphic, let us see what happens then. That is what we are doing. Then we can write it like this, and since h of z0 is equal to 0, we can use the factorization theorem and conclude that this is equal to, the factorization theorem has not come in yet. This is going to be equal to n equal to 1 to infinity a n z minus z0 to the power n. Because the constant term a0 is going to be equal to 0. h of z0 is 0, h of z0 is the constant term, and hence a0 is equal to 0. So, the function now goes from n equal to 1 to infinity, and it is a simple exercise again for you to sit down and check that this tells us that h of z is z minus z0 times summation n is equal to 1 to infinity a n z minus z0 to the power n minus 1 on dz0r, and the power series which is now written here inside this bracket, that will have a radius of convergence exactly the same as the power series written above. This is good because let us now see what happens to whatever is written inside the bracket. Define g of z to be summation n is equal to 1 to infinity a n z minus z0 to the power n minus 1. Then on dz0r minus z0, what do we have? H of z is equal to z minus z0 times f of z. Let me just go up and show you how we had defined our function h. We had defined on dz0r minus z0 h of z to be exactly equal to z minus z0 times f of z, and we have from star this is equal to z minus z0 times g of z, and because z is not equal to z0, we can divide, telling us that f of z is equal to g of z, and this tells us that f has a removable singularity at z0 because g is a function which is holomorphic on dz0r. The only thing that we need to do is to check that our function h is holomorphic. All this was under the assumption that h is holomorphic. If h was holomorphic, we have now concluded that f has a removable singularity at z0. Alright, let us now conclude that H is holomorphic. On dz0R. The root is to apply Morera's theorem. So, or rather a special case of Morera's theorem, wherein we will check that the integral of h along any triangular path is equal to 0, and from that we can conclude that the integral of h over any closed polygonal path is 0, polygonal path in dz0R is 0, and then hence we will be able to conclude that h is holomorphic. So, let me start by stating that we shall use Morera's theorem. Before we get into the generality of any triangle, let us consider special cases and see what happens. So, let us first draw a picture. Suppose this is our disk dz0R. The first thing to note is that if we have a triangle of this type, where z0 is not in the interior or in the convex hull of our triangle, then the triangle is going to be null homotopic, and away from z0 we already know that our function is holomorphic, and therefore Cauchy's theorem will tell us that the integral is 0. So, let me just note that down. If a triangular path, a triangular curve gamma, let me just call it T rather, satisfies the condition that z0 does not belong to T hat, which is the convex hull of T, which will turn out to be this region. If z0 does not belong to the convex hull, then T is null homotopic and integral of h over gamma will turn out to be 0, because away from z0 we already know that our function h is holomorphic, because it is a product of two holomorphic functions. So, we will not be interested in this case, in this triangular path T at all. Let us prove the statement of integral h over gamma being equal to 0 when the triangular path has z0 as one of its vertices. We will address the case of z0 being in the interior and z0 being on the edge of the triangle later. So, let us first consider the case when z0 is a vertex of T. So, the image, let me just leave the earlier image as it is. Let me draw a new image for you. So, the z0 is here. Let me draw a triangle. This is going to be z1, let us say, and this is going to be z2. And let D be equal to the arc length of the curve gamma z0 to z1 to z2 z0. Now, let us pick some w1 and w2, the red points be w1 and w2, and let us complete the line. Let us draw the line joining w1 and w2 and consider the triangle z0 w1 w2 and the quadrilateral w1 z1 z2 w2. The first observation would be that the integral of h of z dz over the triangle T, which is basically T is the same as gamma. Okay, I am going to use these notations interchangeably. So let me just clear the confusion if it is there. Z0 to Z1 to Z2 to 0. This is the curve t, and if you look at the integral of t, this is going to be equal to the integral of h of z dz, where from z0 to w1 to w2 to w2 z0 plus the integral h of z dz, where the integral is over the quadrilateral now. Z0 to W1 has been taken care of, W1 to Z1 to Z2 to W2 to W1. So let me just draw what we just did. The green one captures the first integral, Z0 to W1, W1 to W2, W2 to Z0. And the pink captures W1 to W2, sorry, W1 to Z1, Z1 to W2, Z1 to Z2, Z2 to W2, and finally W2 to W1. If you notice, W1 to W2 and W2 to W1 cancel off each other, and we'll get back our integral of h over t. So, and like we had argued earlier, this region is contained in our domain of definition of h, and hence this is null homotopic. Therefore, the integral by Cauchy's theorem of this particular polygon is going to be equal to 0 by Cauchy's theorem. And therefore, what do we have? Hence, integral of h of z dz over t is the same as the integral h of z dz over gamma z0 to w1 to w2 to z0, the small triangle. Now what we will do is we will use the fact that h is continuous. So that is something which we have already given up as an exercise. So let me just show that exercise to you. We will use this exercise, and around z0 we will be able to get hold of a small neighborhood. So given epsilon positive, let delta positive be such that the absolute value of h of w minus h of z0 is less than epsilon by the arc length. We called the arc length something, right? The arc length was called d. It's bounded by d when absolute value of w minus z0 is less than delta. Notice that h of z0 is 0. So this is actually the same as absolute value of h of w is less than epsilon by d. Now arrange for w1 and w2, pick w1, w2 above, so that gamma z0, w1, w2, z0, this complex hull, the interior as well, is contained in d z0 delta. That can always be done. And then what do we have? Then the absolute value of integral of t h of z dz, which is the same as the absolute value of the integral of gamma z0, w1, w2, z0 of h of z dz. This is going to be less than or equal to, it's less than epsilon by d times the arc length of this triangle, which is bounded by the arc length of t, which is equal to d, and hence this is going to be less than epsilon. So what do we have? Hence the integral over t h of z dz absolute value, this is less than epsilon. Our choice of epsilon was arbitrary, and for epsilon small we will be hence able to conclude, as epsilon converges to 0, we get hence that the integral of h of z dz over t is equal to 0. So let me just go up and show you the picture. In the case when z0 is a vertex of t, we have just concluded that the integral is 0. Let me now show you what happens in the other two cases. When z0 is on an edge of T, we have the following image. Z0 is like this, we have a triangle, and we will do the same trick of partitioning this triangle in this manner. So, we will have first the integral over this small triangle, and the second one would be the integral over this second triangle, and hence we will get the integral over the entire triangle. But by the previous case, we will be able to conclude that both the cases, because it's a vertex, the integral is 0, and hence the integral over this triangle is as well 0. How about when z0 is an interior point? Is in the interior of T hat. That case is covered by drawing more lines and finishing triangles, making it into an edge. If you draw these triangles, then going along this, going along this, and going along this, we will be able to get hold of the triangle, integral over the triangle, which hence is the sum of the integral over the smaller three triangles, each of which is 0, because it has z0 as one of its vertices. So, these cases follow from the case when z0 is a vertex of T. So, I will leave the details to you. It is a very simple check from here, and with that we will be able to conclude by Moreira's theorem that H is a holomorphic function. So, we have completed the proof of Riemann removable singularity theorem here. Yet again, there is some observation to be made here regarding the differences of real valued differentiable functions and complex differentiable or holomorphic functions. If you notice, the function f of x is equal to mod x is locally bounded in a neighborhood of 0, but the corner tells us that we cannot extend the function to 0 as a differentiable function. Such a situation of corners does not arise with holomorphic functions, and that is one major difference again from a real valued differentiable function to a holomorphic function.